Hello there, and welcome. Tonight we'll drift through the quiet history of space travel, from the first trembling rockets to the stations orbiting silently above us. Close your eyes if you like. Let the words wash over you like gentle waves. There's no rush. We have all the time in the universe. The first object humans ever sent into space was a simple metal sphere. On October the 4th, 1957, the Soviet Union launched Sputnik 1 into orbit around Earth. It was barely larger than a beach ball, measuring just 23 inches across, and it weighed only 184 pounds. Yet this small gleaming object changed everything. As it circled the planet, Sputnik transmitted a simple radio pulse, a steady beep that could be picked up by amateur radio operators around the world. That sound, lonely and persistent, announced that humanity had finally broken free from the surface of its home world. The space age had begun not with fanfare, but with a quiet, beeping signal crossing the darkness. For 92 days, Sputnik orbited Earth before its battery died, and it fell silent. 3 months later, it burned up in the atmosphere, leaving only the memory of what it had accomplished. That memory was enough to ignite a race among nations, a competition to reach higher, to travel farther, to explore the vast ocean of space that had always hung above us, waiting. Before humans could go to space, animals paved the way. A small dog named Laika became the first living creature to orbit Earth aboard Sputnik 2 on November 3rd, 1957. She was a stray found wandering the streets of Moscow, chosen for her calm temperament and small size. Laika's journey was one way. The technology to safely return a spacecraft from orbit did not yet exist. Though the true details were not revealed for many years, we now know she survived only a few hours in orbit. Her mission proved that a living being could withstand the forces of launch and the environment of weightlessness, even briefly. Her sacrifice, and that of other animal test subjects, showed scientists what would be needed to protect human astronauts. Other animals followed, including dogs, monkeys, mice, and even fruit flies. Each mission tested different aspects of space travel, from the effects of radiation to the challenges of re-entry. These silent pioneers gave scientists the knowledge they needed to keep humans safe. Their contributions are remembered quietly, honored in the history books that chronicle our first steps beyond Earth. The first human to see Earth from space was Yuri Gagarin. On April the 12th, 1961, the 27-year-old Soviet cosmonaut climbed into the Vostok 1 spacecraft and blasted off from the Baikonur Cosmodrome in Kazakhstan. His journey lasted just 108 minutes, a single orbit around the planet. As he soared above the clouds, Gagarin looked down and saw something no human had ever witnessed: the entire curve of Earth. Against the black of space, the thin blue line of atmosphere that protects all life. The continents and oceans spread below like a living map. He radioed back to ground control, describing the view in words filled with wonder. "The Earth is blue," he said. "How beautiful it is." When he returned safely to the ground, landing by parachute in a field where startled farmers watched him descend, Gagarin became an instant hero. His flight proved that humans could survive in space, that we could leave our planet and return home again. It was a moment of triumph, a confirmation that the universe was not beyond our reach. Less than a month after Gagarin's flight, the United States sent its first astronaut into space. On May 5, 1961, Alan Shepard climbed aboard the Freedom 7 spacecraft, a small capsule perched atop a Redstone rocket. His mission was suborbital, meaning he would not circle the Earth but would arc up into space and then fall back down. The entire flight lasted just 15 minutes and 28 seconds. Shepard reached an altitude of 116 miles, high enough to experience a few minutes of weightlessness and to see the curve of Earth below him. Though brief, his journey was a critical step for the American space program. It showed that the United States could compete in the space race, that American engineers and astronauts could achieve what the Soviets had done. Shepard's calm demeanor during the flight, his steady voice as he reported on instruments and conditions, reassured a nation that had watched the Soviet Union take the lead. The space race was far from over. It was just beginning. John Glenn became the first American to orbit Earth on February 20th, 1962. His spacecraft, Friendship 7, completed 3 orbits in just under 5 hours. As Glenn circled the planet, he witnessed 3 sunrises and 3 sunsets, the sky shifting from brilliant blue to deep black and back again with breathtaking speed. He observed strange glowing particles outside his window, what he described as fireflies dancing around the capsule. These turned out to be frozen droplets of water vapor from the spacecraft's systems, catching the sunlight as they drifted through space. Glenn's mission was not without tension. During re-entry, warning lights suggested that the heat shield, the barrier protecting him from the intense heat of returning through the atmosphere, might be loose. Ground controllers feared the shield could detach, which would have been catastrophic. They instructed Glenn to keep the retro rocket pack attached during re-entry to help hold the shield in place. The tense minutes as the capsule plunged through the atmosphere, surrounded by a sheath of glowing plasma that blocked all radio communication, felt like an eternity. But the heat shield held. Glenn splashed down safely in the Atlantic Ocean, and America had its first orbital hero. The Gemini program taught astronauts how to work in space. Between 1965 and 1966, NASA launched 10 crewed Gemini missions. Each spacecraft carried 2 astronauts and was designed to test the skills that would be needed for a journey to the moon. Astronauts learned how to rendezvous and dock with other spacecraft, how to change orbits, and how to perform spacewalks. The Gemini missions were a training ground, a place to make mistakes and learn from them before attempting something as ambitious as a lunar landing. Gemini 4 saw the first American spacewalk when Ed White opened the hatch and floated outside for just over 20 minutes. He was so enchanted by the experience that he had to be ordered back inside, reluctant to leave the stunning view and the freedom of floating in the void. Gemini 6 and 7 achieved the first space rendezvous, their spacecraft coming within a foot of each other as they orbited Earth together. These accomplishments, quiet and methodical, built the foundation for what came next. The Apollo program aimed to land humans on the moon. President John F. Kennedy had challenged the nation in 1961 to achieve this goal before the decade was out. It seemed almost impossible at the time. The technology did not yet exist. The rockets were not powerful enough. The spacecraft had not been designed. But engineers, scientists, and astronauts worked tirelessly to turn the dream into reality. The Apollo spacecraft consisted of three main parts: a command module where the astronauts lived, a service module that held fuel and supplies, and a lunar module that would actually land on the moon. The Saturn V rocket, the most powerful ever built, would launch them into space. It stood 363 feet tall and generated 7.5 million pounds of thrust at liftoff. When it launched, the ground shook for miles around. The roar was deafening. The sight of it rising into the sky, flames pouring from its engines, was both terrifying and beautiful. This was the machine that would carry humans to another world. Apollo 11 achieved the impossible on July 20th, 1969. Astronauts Neil Armstrong and Buzz Aldrin descended to the moon's surface in the lunar module Eagle, while Michael Collins orbited above in the command module Columbia. As Armstrong guided the lander down, alarms sounded. The computer was overloaded. Fuel was running low. Armstrong had to manually pilot the craft, searching for a safe place to set down among the rocky terrain. With only seconds of fuel remaining, he found a flat spot and gently brought Eagle to rest. His words, transmitted across 240,000 miles of space, were calm and understated. The Eagle has landed. 6 hours later, Armstrong opened the hatch and climbed down the ladder. He placed his boot on the lunar surface, leaving the first human footprint on another world. That's one small step for man, one giant leap for mankind. Aldrin joined him minutes later. Together, they spent 2.5 hours on the moon, collecting rocks, taking photographs, and planting an American flag. The lunar soil was fine and powdery, clinging to their suits. The sky above was black, even in daylight, because the moon has no atmosphere to scatter sunlight. Earth hung in that black sky, a brilliant blue and white marble. They had traveled farther from home than anyone ever had, and yet they could still see home, glowing softly in the darkness. 5 more Apollo missions landed on the moon between 1969 and 1972. Each mission explored a different region, collecting samples and conducting experiments. Apollo 12 demonstrated pinpoint landing accuracy, touching down within walking distance of an old robotic probe. Apollo 15 brought a lunar rover, a battery-powered vehicle that allowed astronauts to travel several miles across the surface. They drove along the edge of craters, climbed the slopes of mountains, and gazed at landscapes no human had ever seen. Apollo 17, the final mission, included geologist Harrison Schmitt, the only scientist to walk on the moon. He collected some of the most scientifically valuable samples of the entire program. Together, the Apollo missions brought back 842 pounds of lunar rocks and soil. These samples are still studied today, revealing secrets about the moon's formation and the early history of the solar system. The footprints left by the astronauts remain on the surface, undisturbed by wind or rain, because the moon has neither. They will last for millions of years, silent markers of humanity's brief visit. Apollo 13 became famous not for landing on the moon, but for surviving a disaster. On April 13th, 1970, 2 days after launch, an oxygen tank in the service module exploded. The astronauts Jim Lovell, Jack Swigert, and Fred Hayes heard a loud bang and felt the spacecraft shudder. Warning lights flashed. Systems began to fail. "Houston, we've had a problem," Swigert reported, words that would become etched in spaceflight history. The explosion had damaged the command module's life support systems. The mission to land on the moon was immediately abandoned. The only goal now was to bring the crew home alive. The astronauts powered down the command module to conserve what little energy remained and moved into the lunar module, using it as a lifeboat. But the lunar module was designed to support 2 people for 2 days, not 3 people for 4 days. Everything had to be rationed: power, water, oxygen. The cabin grew cold. Condensation formed on the walls. Carbon dioxide levels rose dangerously high, forcing the crew to improvise a filter using plastic bags, cardboard, and tape. Ground controllers worked around the clock, testing procedures and guiding the astronauts through each step. The journey home was tense and uncertain. But 4 days after the explosion, Apollo 13 splashed down safely in the Pacific Ocean. It was, in the words of Mission Control, a successful failure. A mission that did not achieve its goal, but demonstrated the courage and ingenuity of both the astronauts and the people who supported them from Earth. The Space Shuttle was the first reusable spacecraft. Unlike the Apollo capsules, which could only be used once, the shuttle was designed to launch like a rocket, orbit Earth like a spacecraft, and land like an airplane. It could be refurbished and flown again, making space travel more routine and affordable. The shuttle had a crew compartment that could carry up to 7 astronauts, a large cargo bay for satellites and equipment, and a robotic arm for deploying and retrieving payloads. On April 12, 1981, the shuttle Columbia lifted off on its maiden flight. Astronauts John Young and Robert Crippen piloted the craft through 2 days in orbit, testing its systems and handling. When they returned, Columbia glided down to a perfect landing on a runway at Edwards Air Force Base in California. The crowd watching erupted in cheers. The dream of a reusable spacecraft had become reality. Over the next 3 decades, the shuttle fleet flew 135 missions, deploying satellites, conducting scientific experiments, and building the International Space Station. The shuttles were marvels of engineering, but they were also fragile. 2 tragic accidents, Challenger in 1986 and Columbia in 2003, claimed the lives of 14 astronauts and reminded the world that space travel is dangerous, that every launch carries risk. The International Space Station is the largest structure humans have ever built in space. It is a collaboration among 5 space agencies from 15 countries, including the United States, Russia, Europe, Japan, and Canada. Construction began in 1998, when the Russian module Zarya was launched into orbit, followed by the American module Unity. Over the next 13 years, more than 40 additional components were added piece by piece during space shuttle missions and Russian rocket launches. Astronauts and cosmonauts worked together, conducting spacewalks to connect modules, install solar panels, and attach equipment. Today, the station spans 356 feet from end to end, about the length of a football field. It weighs nearly 1 million pounds and orbits Earth at an altitude of 250 miles, circling the planet every 90 minutes. Inside, there is more living space than a 6-bedroom house, with sleeping quarters, laboratories, a gym, and a windowed observation module called the cupola that offers breathtaking views of Earth. The station has been continuously inhabited since November 2nd, 2000. Astronauts and cosmonauts from around the world live and work there in rotating crews, typically staying for 6 months at a time. They conduct experiments in biology, physics, astronomy, and materials science, taking advantage of the microgravity environment that cannot be replicated on Earth. Living on the International Space Station requires adapting to a world without up or down. In microgravity, there is no weight, no sense of falling, just a constant sensation of floating. Astronauts sleep in small sleeping bags attached to the walls, drifting gently in their dreams. They eat food from pouches and cans, using straws for liquids and forks for solids. Loose crumbs are dangerous because they can float into sensitive equipment or be inhaled, so bread is forbidden. Tortillas are used instead because they do not crumble. Water behaves strangely in microgravity, forming floating spheres that wobble and shimmer in the air. Astronauts drink by sucking water from bags, and they wash using wet towels because showers would create floating droplets everywhere. Exercise is essential. Without the constant pull of gravity, muscles and bones weaken, losing mass at an alarming rate. Astronauts work out at least 2 hours every day on treadmills, stationary bikes, and resistance machines, all specially designed for use in space. Even going to the bathroom is complicated. Toilets use airflow instead of gravity to pull waste away from the body, and everything must be carefully contained and stored. Despite these challenges, astronauts describe life on the station as magical. They float through modules, somersaulting in the air, peering out windows at the Earth spinning below, watching thunderstorms light up the night side of the planet, seeing the aurora shimmer in the thin atmosphere. The station travels at 17,500 miles per hour. At this speed, it completes an orbit of Earth every 90 minutes, which means the crew experiences 16 sunrises and 16 sunsets every day. The sun rises over the horizon, flooding the station with brilliant light. Then 45 minutes later it sets, plunging everything into darkness. The rapid cycle makes it difficult to maintain a normal sleep schedule, so the station uses artificial lighting and schedules to help the crew stay on a 24-hour routine. From the cupola, astronauts can see the entire arc of the planet, the continents and oceans, the swirling clouds, the thin blue line of the atmosphere. They see deserts glowing golden in the sunlight, mountain ranges casting long shadows, rivers winding through green valleys. At night, cities light up like constellations, their streets and buildings glowing against the dark. The station itself is visible from Earth. On a clear night, if you know where and when to look, you can see it passing overhead, a bright point of light moving steadily across the sky. It is the third brightest object in the night sky after the Moon and Venus. A reminder that humans live and work up there, floating above us. Spacewalks are among the most dangerous and demanding tasks astronauts perform, also called extravehicular activities, or EVAs. These excursions require astronauts to leave the safety of the spacecraft and work in the vacuum of space. The first spacewalk was performed by Soviet cosmonaut Alexei Leonov on March 18, 1965. He floated outside the Voskhod 2 capsule for 12 minutes, tethered by a lifeline. It was a terrifying experience. His spacesuit inflated in the vacuum, becoming so stiff that he could barely move. When it came time to re-enter the airlock, he could not fit through the narrow opening. He had to release some of the pressure from his suit, risking decompression sickness in order to squeeze back inside. 3 months later, American astronaut Ed White performed the first US spacewalk during the Gemini 4 mission. He spent just over 20 minutes outside, maneuvering with a small handheld jet gun. White was so captivated by the experience that he was reluctant to return to the spacecraft, calling it the saddest moment of his life when he was ordered back inside. Spacewalks are necessary for tasks that cannot be done by robotic arms, such as repairing equipment, installing new components, or conducting experiments. Before performing a spacewalk, astronauts spend months training underwater in a massive pool called the Neutral Buoyancy Laboratory. The pool holds 6 million gallons of water and contains full-scale replicas of parts of the International Space Station. Underwater, astronauts practice the exact tasks they will perform in space, learning how to move in a bulky spacesuit, how to use specialized tools, and how to work efficiently while tethered to the station. Divers hover nearby to assist if anything goes wrong. For every hour an astronaut spends on a spacewalk, they train for about 7 hours in the pool. The training is exhausting, but essential. The spacesuits worn during EVAs are marvels of engineering. Each suit, called an extravehicular mobility unit, is essentially a miniature spacecraft. It provides oxygen to breathe, removes carbon dioxide, regulates temperature, protects against radiation and micrometeoroids, and maintains pressure so the astronaut's body does not suffer the effects of vacuum. The suit has multiple layers, including a bladder to hold pressure, insulation to regulate temperature, and an outer layer made of tough fabric to resist tears. The helmet has a gold-coated visor to protect against the sun's glare. Inside the suit, a system of tubes circulates cool water to prevent overheating. Despite all this protection, spacewalks are risky. Temperatures outside the station range from plus 250 degrees Fahrenheit in direct sunlight to minus 250 degrees in shadow. A small tear in the suit could be fatal. Astronauts must move carefully, always staying tethered to the station, always aware of their surroundings. In case of emergency, the suit has a small jetpack called Safer, that can propel an astronaut back to the station if they become untethered. More than 270 spacewalks have been conducted at the International Space Station since its construction began. Some have lasted more than 8 hours. Astronauts have installed solar panels, repaired cooling systems, replaced batteries, and upgraded scientific instruments. They have worked in pairs, communicating with each other and with mission control on Earth, carefully following procedures to ensure safety and success. Each spacewalk is carefully choreographed, every movement planned and practiced. Yet there is always an element of unpredictability. Tools can slip from gloved hands and float away into space. Unexpected problems can arise. In 2013, Italian astronaut Luca Parmitano's helmet began filling with water during a spacewalk, a dangerous malfunction that forced him to return to the airlock immediately. He made it back safely, but the incident was a stark reminder of the risks involved. Rockets are the only way to reach space from Earth. Unlike airplanes, which rely on the atmosphere to generate lift, rockets work by expelling mass at high speed in one direction, which propels the rocket in the opposite direction. This is Newton's third law of motion. For every action, there is an equal and opposite reaction. Rockets carry both fuel and an oxidizer, which allows them to burn in the vacuum of space where there is no oxygen. The combustion produces hot gases that are expelled through a nozzle at the back of the rocket, creating thrust. The faster the gases are expelled, the more thrust is generated. To escape Earth's gravity and reach orbit, a rocket must accelerate to at least 17,500 miles per hour, about 25 times faster than the speed of a commercial jet. This requires an enormous amount of energy. Most of a rocket's mass at launch is propellant. The spacecraft and payload, the actual object being sent into space, make up only a small fraction of the total weight. This is why rockets are often built in stages. Each stage contains its own engines and fuel tanks. When the fuel in one stage is exhausted, that stage is jettisoned, falling away and reducing the weight the remaining stages must carry. This makes the rocket more efficient. The Saturn V, which launched the Apollo missions to the Moon, had 3 stages. By the time it reached orbit, the first 2 stages had been discarded, and only the 3rd stage and the spacecraft remained. Modern rockets come in many designs. Some use liquid fuel, which can be controlled and throttled during flight. Liquid fuel engines are complex, requiring pumps, valves, and precise engineering, but they offer great flexibility. The Space Shuttle's main engines were liquid-fueled, burning liquid hydrogen and liquid oxygen to produce over 1 million pounds of thrust. Other rockets use solid fuel, a pre-mixed propellant that burns like a giant firework. Solid fuel rockets are simpler and more reliable, but once ignited, they cannot be shut off or throttled. The Space Shuttle also used 2 solid rocket boosters to help lift it into space. These boosters provided much of the thrust during the first 2 minutes of flight, before burning out and parachuting back to Earth to be recovered and reused. Today, new companies are developing reusable rockets that can land vertically after launch and be flown again. SpaceX, a private aerospace company, has successfully landed and reused its Falcon 9 rockets dozens of times, dramatically reducing the cost of reaching space. The sight of a rocket descending from the sky, engines blazing, and landing gently on a platform is both futuristic and surreal. A glimpse of how routine space travel might become. Mars has captured human imagination for centuries. The Red Planet, as it is often called because of its rusty-colored surface, has long been thought of as a possible home for life. In the late 19th and early 20th centuries, astronomers believed they saw canals on Mars, straight lines crisscrossing the surface, which some speculated were built by an advanced civilization. These canals turned out to be optical illusions, but the idea that Mars might harbor life persisted. In recent decades, robotic explorers have revealed a world that is both familiar and alien. A cold desert with towering volcanoes, vast canyons, and ancient riverbeds that suggest water once flowed across its surface. Understanding Mars, learning its history, searching for signs of life, these are some of the greatest scientific quests of our time. The first successful mission to Mars was Mariner 4, which flew past the planet in July 1965 and sent back the first close-up images. They showed a barren, cratered landscape, more like the Moon than Earth. The images were disappointing to those who had hoped for a vibrant world, but they were scientifically invaluable. Over the following decades, more spacecraft visited Mars, orbiting the planet and mapping its surface. In 1976, NASA's Viking 1 and Viking 2 became the first spacecraft to successfully land on Mars. They sent back stunning photographs of the Martian surface, a rocky plain beneath a pink sky. The sky appears pink because of dust suspended in the thin atmosphere. The Vikings also conducted experiments to search for signs of life in the soil, but the results were inconclusive. In 1997, Mars Pathfinder landed on the planet and deployed Sojourner, the first rover to explore Mars. Sojourner was small, about the size of a microwave oven, and it moved slowly, analyzing rocks and soil with its instruments. It was a proof of concept, showing that rovers could work on Mars. The mission was a success, and it paved the way for more ambitious rovers. In 2004, NASA landed 2 rovers, Spirit and Opportunity, on opposite sides of Mars. They were designed to last 90 days. Spirit operated for over 6 years, and Opportunity continued working for nearly 15 years, far exceeding all expectations. These rovers traveled for miles across the Martian surface, climbing hills, exploring craters, and analyzing hundreds of rocks. They found clear evidence that water once existed on Mars, minerals that form only in the presence of water, patterns in rocks that suggest ancient streams and lakes. This discovery was profound. It meant that Mars, now a frozen desert, was once warmer and wetter, possibly capable of supporting life. Curiosity, a car-sized rover, landed on Mars in August 2012. It carried a sophisticated suite of instruments, including cameras, spectrometers, a drill, and a small chemistry lab. Curiosity's mission was to determine whether Mars ever had the conditions necessary to support microbial life. It landed in Gale Crater, a massive impact basin with a towering mountain of layered rock at its center. As Curiosity climbed the slopes of this mountain, it drilled into rocks and analyzed the samples. It found organic molecules, the building blocks of life preserved in ancient mudstones. It detected methane in the atmosphere, a gas that on Earth is often produced by living organisms, though it can also have geological sources. Curiosity confirmed that Gale Crater once held a lake, a body of water that persisted for millions of years, with conditions that could have supported life. These findings do not prove that life existed on Mars, but they show that the planet was habitable in the distant past. In February 2021, Perseverance, the newest Mars rover, landed in Jezero Crater, the site of an ancient river delta. Perseverance is searching for signs of ancient life, studying the geology and climate of Mars, and collecting samples of rock and soil that will one day be returned to Earth for detailed analysis. It also carries a small helicopter called Ingenuity, the first aircraft to fly on another planet. Ingenuity made its first flight on April 19, 2021, hovering 10 feet above the Martian surface for 39 seconds. It was a remarkable achievement, a demonstration that powered flight is possible in Mars's thin atmosphere, which is only 1% as dense as Earth's. Ingenuity has since completed dozens of flights, scouting ahead for the rover and testing technologies that could be used in future missions. Sending humans to Mars is one of the great challenges of our time. Unlike the Moon, which is only 3 days away, Mars is months distant. At its closest, Mars is about 35 million miles from Earth. But the planets orbit the Sun at different speeds, so the distance changes constantly. A mission to Mars would take 6 to 9 months each way, and astronauts would need to stay on the surface for over a year, waiting for the planets to align again for the return journey. The total mission could last 2 to 3 years. During that time, astronauts would face numerous dangers: intense radiation from cosmic rays and solar flares, the physical effects of prolonged weightlessness, the psychological challenges of isolation and confinement. They would need to bring or produce all their own food, water, and oxygen. They would need habitats that protect them from the harsh Martian environment, where temperatures plunge to -100 degrees Fahrenheit at night, and the atmosphere is too thin to breathe. The surface is covered in fine dust that could damage equipment and harm lungs if inhaled. Despite these challenges, plans are underway. NASA's Artemis program aims to return humans to the Moon as a stepping stone to Mars, using the Moon as a testing ground for the technologies and techniques that will be needed. Private companies like SpaceX are developing the massive rockets and spacecraft that could carry astronauts to Mars. The dream of walking on the red planet, of planting a flag in its soil and looking up at Earth as a pale blue dot in the Martian sky, is no longer science fiction. It is a goal that many hope might be achieved within the next few decades, though the exact timeline remains uncertain. The Moon is Earth's constant companion. It has orbited our planet for over 4 billion years, formed from debris after a massive collision between the young Earth and a Mars-sized object. The moon's gravity stabilizes Earth's rotation, which helps maintain a stable climate. It creates the tides, the rhythmic rise and fall of the oceans, which have shaped coastlines and influenced life for eons. At night, it lights up the sky, reflecting sunlight across the darkness. For most of human history, the moon was an object of wonder and mystery, worshipped, studied, and dreamed about. In 1969, we finally reached it. Now, more than 50 years later, we are preparing to return. The Artemis program, named after the twin sister of Apollo in Greek mythology, aims to land the first woman and the next man on the moon. While initial plans targeted the mid-2020s, the timeline has shifted as the program develops. Unlike Apollo, which focused on short visits to demonstrate capability, Artemis is designed for long-term exploration. The goal is to establish a sustainable presence on the moon, with habitats, rovers, and infrastructure that will allow astronauts to live and work there for extended periods. The lunar South Pole is the target, a region that has never been visited by humans. It contains permanently shadowed craters where ice may be trapped, ice that could be mined for water, oxygen, and even rocket fuel. The South Pole also has areas that are almost always in sunlight, ideal for solar power. These resources make the region attractive for establishing a lunar base. Artemis will also involve building a small space station called Gateway that will orbit the moon, serving as a staging point for missions to the surface. Astronauts will travel to Gateway, then descend to the moon in a lander, conduct their work, and return to Gateway before heading back to Earth. This architecture is more complex than Apollo, but it is designed for sustainability, allowing repeated missions rather than one-time visits. Beyond the moon lies the rest of the solar system, a vast collection of planets, moons, asteroids, and comets. Robotic spacecraft have visited every planet, sending back images and data that have transformed our understanding of these distant worlds. Voyager 1 and Voyager 2, launched in 1977, flew past Jupiter, Saturn, Uranus, and Neptune, revealing details of their atmospheres, rings, and moons. Voyager 1 is now in interstellar space, the region beyond the influence of the Sun, making it the most distant human-made object. Cassini orbited Saturn for 13 years, studying its majestic rings and discovering geysers of water erupting from the icy moon. Enceladus, a sign of a subsurface ocean that might harbor life. Juno is currently orbiting Jupiter, peering beneath its thick clouds to study its powerful magnetic field and swirling storms. New Horizons flew past Pluto in 2015, showing us a world more complex and beautiful than anyone had imagined, with towering mountains of ice, plains of frozen nitrogen, and a thin atmosphere. These missions are journeys of discovery, revealing the diversity and wonder of the worlds that share our solar system. Astronaut training is rigorous and demanding. Those selected for astronaut programs undergo years of preparation before they are assigned to a mission. They must learn to operate spacecraft systems, to work in microgravity, to perform spacewalks, to conduct scientific experiments. They train in simulators that replicate the conditions of launch, orbit, and re-entry. They practice in underwater pools to prepare for spacewalks. They study Russian because the International Space Station is a collaboration between nations, and crew members must be able to communicate. They undergo survival training, learning to survive in remote environments, in case their spacecraft lands off course. They fly in high-performance jets to maintain their skills and to experience high G-forces. They learn geology, astronomy, medicine, engineering. The training is intense, but those who become astronauts describe it as the opportunity of a lifetime. They are explorers, pioneers, continuing the long tradition of those who ventured into the unknown. The future of space travel is full of possibilities. Companies are developing space tourism, offering flights that will take ordinary people to the edge of space or even into orbit. The cost is high, but it is decreasing. One day, trips to space might be as routine as flying across the ocean. Governments and private companies are planning missions to asteroids, small rocky bodies that contain metals and minerals worth trillions of dollars. Mining these resources could transform the economy and provide the raw materials needed to build structures in space. There are plans to build habitats on the Moon and Mars, places where humans can live and work for years. There are even concepts for interstellar missions, spacecraft that could travel to other star systems, journeys that would take centuries or longer. These are dreams today, but they are grounded in real science and engineering. Each step we take, each mission we fly, brings us closer to a future where humanity is not confined to one planet, but spread across the solar system and perhaps beyond. Space travel has changed how we see ourselves. The images of Earth taken from space, the blue marble photograph from Apollo 17, the pale blue dot captured by Voyager 1 from the edge of the solar system. These images have shown us our planet as it truly is. A small, fragile world suspended in the vast darkness. They have reminded us that we are all passengers on the same spaceship, that the borders and divisions we create are invisible from space, that the atmosphere protecting us is thin and delicate. This perspective, sometimes called the overview effect, has inspired movements for environmental protection, international cooperation, and peace. It has shown us that we are part of something much larger, a universe filled with wonder, mystery, and possibility. So tonight, as you drift towards sleep, think about the quiet journeys happening above you. The International Space Station crossing the sky, the rovers on Mars, exploring ancient riverbeds under a pink sky, the Voyager spacecraft still sending signals from the edge of the solar system, the rockets lifting off from Earth, carrying satellites, supplies, and dreams. Think about the astronauts who have looked back at Earth and seen it whole, who have walked on the Moon and left footprints that will last for eons. Think about the engineers and scientists who solved impossible problems, who turned visions into reality. And think about the future, the missions yet to come, the discoveries waiting to be made, the worlds waiting to be explored. Let the vastness of space cradle you. Let the silence between the stars quiet your mind. We have traveled so far, from that first beeping satellite to footprints on the moon to rovers on Mars. And we are still reaching, still dreaming, still moving forward into the great unknown. The universe is patient. It has waited billions of years. It will wait for us. Rest now. Let your thoughts float like an astronaut in microgravity. Let the rhythm of the Earth spinning beneath you, completing one rotation every 24 hours, lull you into peace. The stars are still there, glowing softly in the darkness. The moon is still there, casting its gentle light. And somewhere, high above, the International Space Station continues its endless orbit, a small outpost of humanity in the vast ocean of space. The journey to becoming an astronaut begins with selection. NASA receives thousands of applications whenever it opens recruitment, but only a handful are chosen. The requirements are strict. Applicants must have at least a bachelor's degree in science, technology, engineering, or mathematics. They must have relevant professional experience or advanced degrees. They need excellent physical health, meeting demanding medical standards. Vision, blood pressure, height, all are evaluated. Beyond the technical requirements, NASA looks for people who work well in teams, who stay calm under pressure, who can adapt to unexpected situations. The selection process includes multiple rounds of interviews, medical examinations, and psychological evaluations. Those who make it through become astronaut candidates and begin 2 years of basic training before they can even be assigned to a mission. The training covers everything from spacecraft systems to geology to survival skills. Candidates learn to fly T-38 jets, maintaining proficiency in high-speed aviation. They study the mechanical systems of the International Space Station, memorizing procedures for normal operations and emergencies. They practice using the robotic arm, the Canadarm2, which is essential for capturing visiting spacecraft and moving equipment outside the station. They train in simulators, running through countless scenarios until their responses become automatic. The training is exhausting, mentally and physically demanding, but those who complete it join an elite group. Since the beginning of human spaceflight, fewer than 600 people have traveled to space. It is one of the rarest experiences a human can have. The spacesuits used today are technological marvels. The Extravehicular Mobility Unit, or EMU, used for spacewalks from the International Space Station, weighs about 300 pounds on Earth, though in the weightlessness of space, it has no weight at all. It consists of multiple layers, each serving a specific function. The innermost layer is a liquid cooling garment, covered in tubes that circulate cold water to remove body heat. Without this cooling system, an astronaut would quickly overheat from their own exertion and the heat of the sun. The next layers provide pressure, maintaining the necessary atmospheric pressure to keep the astronaut's body fluids from boiling in the vacuum of space. outer layers offer protection from micrometeoroids, tiny particles traveling at thousands of miles per hour that could puncture the suit. The outermost layer is made of a special fabric that reflects sunlight and insulates against temperature extremes. The helmet has multiple layers as well, including a gold-coated visor that protects the astronaut's eyes from the sun's intense glare. Inside the helmet, a system provides fresh oxygen, removes carbon dioxide, and regulates humidity to prevent the visor from fogging. The gloves are perhaps the most complex part of the suit, designed to allow dexterity while maintaining pressure and protection. Astronauts can grasp tools, operate switches, and perform delicate tasks even though their hands are encased in pressurized gloves. Each suit is custom, fitted to the astronaut who will wear it, adjusted for arm length, torso size, and other measurements. Putting on the suit is a lengthy process, requiring assistance and careful checks to ensure every seal is tight, every connection secure. Once sealed inside, the astronaut is entirely self-contained, carrying their own atmosphere, their own life support, everything they need to survive in the void. The Neutral Buoyancy Laboratory in Houston, Texas, is where astronauts prepare for spacewalks. This massive indoor pool holds 6.2 million gallons of water and is 40 feet deep. Inside the pool are full-scale replicas of sections of the International Space Station, submerged so that astronauts can practice working on them. When an astronaut is suited up and lowered into the water, divers add or remove weights until the astronaut is neutrally buoyant, neither sinking nor floating. In this state, they can simulate the weightlessness of space, maneuvering around the mock-ups, practicing the tasks they will perform on an actual spacewalk. Divers hover nearby, ready to assist if the astronaut becomes tangled, overheated, or needs help. The training sessions can last 6 hours or more, matching the duration of a real spacewalk. Astronauts practice using tools, tightening bolts, connecting cables, all while wearing the bulky suit that restricts movement. They learn to move slowly and deliberately, to plan each motion, because in space there is no friction to stop unwanted motion. If an astronaut pushes too hard against a surface, they will drift away. If they drop a tool, it will float off into the void. Every action must be controlled, every movement intentional. The training is exhausting, but it prepares astronauts for the reality of working in space. Spacecraft returning to Earth face one of the most dangerous phases of any mission: re-entry. When a spacecraft in orbit wants to return, it must slow down, reducing its speed so that it falls back into the atmosphere. This is accomplished by firing retro rockets, small engines that push in the opposite direction of travel. As the spacecraft descends, it encounters the upper atmosphere, a region where the air is still very thin, but dense enough to create friction. The spacecraft is traveling at over 17,000 miles per hour, and the friction with the air generates enormous heat. The temperatures on the heat shield, the protective barrier on the underside of the spacecraft, can reach 3,000 degrees Fahrenheit, hot enough to melt steel. The heat shield is made of special materials designed to ablate, slowly burning away to carry heat with them, protecting the crew inside. As the spacecraft descends, it is surrounded by a sheath of glowing plasma, ionized gas that blocks radio signals. For several minutes, Mission Control loses contact with the crew, a tense period called the blackout. During this time, the astronauts are on their own, trusting that the heat shield will hold, that the calculations are correct. When the spacecraft slows enough, parachutes deploy, further reducing its speed. Finally, it touches down, either on land or in the ocean, depending on the spacecraft design. The astronauts, who moments before were traveling faster than a speeding bullet, are safely home. The transition from the silence of space to the noise and bustle of Earth is jarring. Gravity returns with a vengeance, pulling on their bodies, making every movement feel heavy. Astronauts who have spent months in space must readjust to walking, to standing, to the simple act of living with weight. The readjustment can take weeks or months. The effects of long-duration spaceflight on the human body are significant and still not fully understood. In microgravity, muscles and bones do not have to work as hard to support the body. Over time, they begin to weaken and lose mass. Astronauts can lose up to 1% of their bone density per month in space, a rate similar to osteoporosis. To counteract this, they exercise rigorously, spending at least 2 hours every day on treadmills, stationary bikes, and resistance machines. The equipment is specially designed for microgravity, using bungee cords and other systems to simulate weight. Even with exercise, some bone and muscle loss is inevitable. Astronauts also experience changes in their cardiovascular systems. Without gravity pulling blood toward their feet, fluids shift upward, causing their faces to become puffy and their legs to become thinner. The heart does not have to work as hard to pump blood, and over time, it can become deconditioned. Vision changes are another concern. Many astronauts experience a condition where the pressure inside their eyes increases, flattening the eyeball and causing blurred vision. Some of these changes are temporary, reversing after the astronaut returns to Earth, but others may be permanent. Radiation is another risk. Earth's magnetic field and atmosphere protect us from much of the cosmic radiation that permeates space. But astronauts on the International Space Station receive higher doses. On a mission to Mars, far from Earth's protective bubble, radiation exposure would be even greater, increasing the risk of cancer and other health problems. Scientists are studying these effects, developing countermeasures, medicines, exercises, shielding materials, anything that can help keep astronauts healthy during long missions. The food astronauts eat in space has come a long way since the early days. In the Mercury and Gemini programs, astronauts ate squeezable tubes of pureed food and bite-sized cubes. The food was nutritious but not particularly appetizing. Today, astronauts on the International Space Station have a much wider variety of options. Meals are carefully planned to provide balanced nutrition with a mix of proteins, carbohydrates, fats, vitamins, and minerals. Many foods are freeze-dried to reduce weight and volume. To prepare them, astronauts add water and heat them in a special oven. There are also thermostabilized foods, similar to canned goods, that can be eaten straight from the pouch. Fresh fruits and vegetables are a rare treat brought up on resupply missions, but they do not last long. Astronauts can choose from hundreds of different menu items, including entrees like beef stew, chicken teriyaki, and macaroni and cheese, as well as snacks like nuts, granola bars, and cookies. There are condiments, salt and pepper in liquid form so they do not float away, hot sauce, ketchup. Drinks come in powder form and are mixed with water, coffee, tea, juice, even Tang, the orange-flavored drink that became famous during the Apollo missions. Eating in microgravity requires some adjustments. Food must be secured to trays with Velcro or magnets. Liquids are drunk through straws or from specially designed pouches. Crumbs are avoided because they can float into equipment or be inhaled. Despite the challenges, mealtime is an important part of the day, a chance for the crew to gather, to share stories, to enjoy a moment of normalcy in the extraordinary environment of space. Sleep in space is different. There is no bed to lie in, no pillow to rest your head on. Astronauts sleep in small sleeping bags attached to the walls of the station. They zip themselves in and float gently, drifting in their dreams. Some astronauts prefer to sleep near a window so they can see the Earth and stars. Others prefer the quiet darkness of a closed sleeping compartment. Because the station experiences 16 sunrises and sunsets each day, the crew uses blackout shades and follows a 24-hour schedule to maintain a normal sleep-wake cycle. Sleeping in microgravity can be disorienting. There is no sensation of lying down, no feeling of resting on a mattress. Some astronauts report vivid dreams, perhaps because of the unique environment or the shift in blood flow to the brain. Noise is a constant challenge. The station is filled with the hum of fans, the whir of pumps, the clicks and beeps of equipment. Earplugs help, but some sounds penetrate. Despite these challenges, most astronauts adapt and sleep reasonably well, though they often say that nothing compares to the comfort of sleeping in a real bed with gravity holding you down. The toilets on the International Space Station are one of the most frequently asked about features. Without gravity, waste does not fall away from the body. Instead, the toilet uses airflow to pull waste into a collection system. Solid waste is stored in sealed containers and eventually loaded onto cargo spacecraft that burn up during re-entry over the ocean. Urine is processed through a complex filtration and purification system that recycles it into drinking water. This might sound unpleasant, but the water is cleaner than most tap water on Earth. The recycling system is essential for long-duration missions because launching water into space is expensive and impractical. Every drop that can be reused reduces the amount that needs to be brought from Earth. Astronauts joke about drinking yesterday's coffee, but the system works remarkably well. The recycled water is tested regularly to ensure it meets strict safety standards. The psychological challenges of living in space are just as important as the physical ones. Astronauts live in a confined space, separated from family and friends, surrounded by the same small group of people for months at a time. They cannot step outside for fresh air, cannot take a walk in a park, cannot escape to solitude when they need it. Communication with Earth is possible, but there is a delay, and conversations feel different over a video link. Homesickness, isolation, and the stress of constant work can take a toll. To help crew members cope, mission planners ensure they have time for leisure activities, opportunities to talk with psychologists, regular video calls with loved ones. Astronauts bring personal items, photos, music, books, small reminders of home. They celebrate birthdays and holidays on the station, decorating modules, sharing meals, creating moments of joy and connection. The view from the cupola, the windowed observation module, is often described as therapeutic. Astronauts float there, gazing at the Earth spinning below, watching storms and sunsets, seeing the beauty of their home planet from a perspective few ever experience. It reminds them why they are there, why the work is important. Space has no sound. On Earth, sound travels through the air, vibrations that our ears detect as noise. In the vacuum of space, there is no air, no medium for sound to travel through. The explosions and roars we hear in science fiction movies are pure imagination. In reality, space is silent. Astronauts on a spacewalk cannot hear the hiss of their life support systems, except as vibrations conducted through their bodies. They cannot hear the clang of metal on metal when they work on the station's exterior. They communicate through radios, their voices transmitted electronically. Inside the station, there is sound because there is air, but it is different. Sounds are muffled, and there is a constant background hum of machinery. The silence of space, when astronauts think about it, is profound and eerie, a reminder of how hostile the environment truly is. Temperature in space is a paradox. In direct sunlight, temperatures can soar to over 250 degrees Fahrenheit. In shadow, they plunge to minus 250 degrees. The extremes are caused by the lack of atmosphere. On Earth, the atmosphere absorbs and distributes heat, moderating temperatures. In space, there is nothing to do this. Sunlight heats surfaces directly, and in the absence of light, heat radiates away quickly into the cold void. Spacecraft must be carefully designed to manage these extremes. The International Space Station has radiators that release excess heat and insulation that retains warmth when needed. Astronauts on spacewalks experience these temperature swings, their suits heating up in sunlight and cooling rapidly in shadow. The liquid cooling garment inside the suit helps regulate their body temperature, but they must be mindful of where they work and how long they stay exposed to either extreme. The space environment also contains radiation. Earth's magnetic field and atmosphere protect us from most of the harmful radiation that comes from the sun and distant cosmic sources. In space, that protection is greatly reduced. The International Space Station orbits within Earth's magnetic field, which offers some shielding, but astronauts still receive higher radiation doses than they would on the ground. On a mission to the Moon or Mars, Far from Earth's magnetic protection, the radiation exposure would be much greater. Solar flares, massive eruptions on the sun's surface, can release bursts of radiation that are particularly dangerous. Spacecraft must be designed with shielding, and astronauts must have safe areas to retreat to during solar storms. Long-term exposure to radiation increases the risk of cancer and can cause other health problems. Scientists are working on better shielding materials, protective medications, and monitoring systems to keep astronauts as safe as possible. Micrometeoroids and orbital debris pose another threat. Space around Earth is not empty. It is filled with tiny particles, bits of rock and metal traveling at thousands of miles per hour. Some of these are natural, fragments of asteroids and comets that have been wandering the solar system for billions of years. Others are human-made, pieces of old satellites, fragments from rocket stages, flecks of paint, all the detritus of decades of space exploration. These particles, though small, can cause significant damage because of their incredible speed. A fleck of paint traveling at 17,000 miles per hour carries as much energy as a bowling ball thrown at 60 miles per hour. The International Space Station has shielding to protect against small particles, layers of material designed to absorb and dissipate the energy of impacts. Larger pieces of debris are tracked from the ground, and if one is predicted to come too close, the station can maneuver out of the way, firing its thrusters to change orbit. These maneuvers are relatively common, a reminder that space, though vast, is increasingly crowded near Earth. The problem of space debris is growing. Every satellite launched, every rocket stage left in orbit adds to the accumulation. When two objects collide, they shatter into thousands of smaller pieces, each one a potential hazard. This could lead to a cascade effect, where collisions create more debris, which causes more collisions, eventually making certain orbits unusable. This scenario is sometimes called the Kessler syndrome, named after the NASA scientist who first described it. To prevent this, international guidelines encourage operators to deorbit satellites at the end of their lives, either by bringing them back into the atmosphere where they burn up, or by moving them to graveyard orbits where they will not interfere with active spacecraft. But enforcement is difficult, and not all countries and companies follow these guidelines. Efforts are underway to develop technologies for removing debris, nets and harpoons that could capture defunct satellites, robotic arms that could grab and deorbit old rocket stages. Cleaning up space is essential if we want to continue using it for exploration, communication, and science. Communication with spacecraft is a complex challenge. Radio waves travel at the speed of light, but space is so vast that even at this incredible speed, there can be significant delays. Communicating with the International Space Station, which orbits about 250 miles above Earth, is almost instantaneous. But communicating with a rover on Mars requires patience. When Earth and Mars are at their closest, radio signals take about 4 minutes to travel from one planet to the other. At their farthest, the delay can be over 20 minutes. This means that a conversation with a rover on Mars is impossible. Commands are sent, and then controllers wait for the rover to execute them and send back a response. If something goes wrong, the rover must handle it on its own, at least for the time it takes signals to travel back and forth. The Voyager spacecraft, now beyond the edge of the solar system, is so far away that radio signals take over 22 hours to reach it. Despite the distance, Voyager still sends back data, a faint signal detected by massive radio dishes on Earth. The fact that we can still communicate with a spacecraft launched in 1977, billions of miles away, is a testament to the ingenuity of the engineers who designed it and the dedication of those who continue to operate it. The Deep Space Network is the system that communicates with spacecraft beyond Earth orbit. It consists of 3 facilities located around the world, in California, Spain, and Australia. These locations are spaced roughly 120 degrees apart, so that as Earth rotates, at least one facility is always able to see a spacecraft in deep space. Each facility has massive radio antennas, some over 200 feet in diameter, capable of detecting incredibly faint signals. The network is constantly busy, tracking missions to Mars, Jupiter, Saturn, and beyond, as well as spacecraft exploring asteroids, comets, and the outer reaches of the solar system. Scheduling time on the Deep Space Network is a precious commodity, and mission planners must carefully coordinate to ensure all spacecraft get the communication time they need. The cost of space exploration is enormous. Launching a single kilogram of payload into low Earth orbit can cost thousands of dollars. A mission to Mars can cost billions. The International Space Station has cost over $150 billion to build and operate, making it one of the most expensive structures ever created. These costs are justified by the scientific knowledge gained, the technological advancements developed, and the inspiration provided to future generations. Space exploration drives innovation. Technologies developed for spacecraft, such as water purification systems, advanced materials, medical devices, and communication satellites, have found applications on Earth, improving lives in countless ways. The investment in space pays dividends far beyond the missions themselves. Private companies are playing an increasing role in space exploration. SpaceX, Blue Origin, and other companies are developing rockets and spacecraft, competing for contracts to launch satellites, resupply the International Space Station, and eventually carry astronauts. This commercial involvement is reducing costs and increasing access to space. SpaceX's Falcon rockets, which can land and be reused, have dramatically lowered the price of reaching orbit. The company is also developing Starship, a massive, fully reusable spacecraft designed to carry humans to the Moon, Mars, and beyond. Blue Origin, founded by Jeff Bezos, is working on reusable rockets and spacecraft as well, with a focus on both cargo and tourism. Other companies are developing small satellites, space habitats, mining technologies, and more. The rise of commercial spaceflight is opening new possibilities, making space more accessible than ever before. Space tourism is becoming a reality. In 2001, Dennis Tito became the first space tourist, paying $20 million to spend 8 days on the International Space Station. Since then, a handful of other wealthy individuals have made similar trips. More recently, companies like SpaceX, Blue Origin, and Virgin Galactic have offered suborbital and orbital flights to private citizens. These flights are expensive, but they represent the beginning of a new era where space travel is not limited to professional astronauts. Suborbital flights, which reach the edge of space but do not complete an orbit, offer a few minutes of weightlessness and stunning views of Earth against the black of space. Orbital flights, which circle the Earth, offer a longer experience, days in microgravity, opportunities to see the planet from above, and the thrill of traveling at 17,000 miles per hour. As technology improves and costs decrease, space tourism is expected to become more common, allowing more people to experience the wonder of space. The Hubble Space Telescope has transformed our understanding of the universe. Launched in 1990 aboard the Space Shuttle Discovery, Hubble orbits Earth at an altitude of about 340 miles above the distorting effects of the atmosphere. Its position gives it an incredibly clear view of the cosmos. Over the past 3 decades, Hubble has captured images of distant galaxies, nebulae where stars are born, the remnants of supernova explosions, and planets in our own solar system. It has helped determine the age of the universe, measured the rate at which the universe is expanding, and provided evidence for the existence of dark energy. Hubble has observed some of the most distant objects ever seen, galaxies so far away that their light has been traveling for billions of years to reach us. These observations show us the universe as it was in the distant past, offering glimpses of the early cosmos. Hubble has been serviced and upgraded multiple times by space shuttle crews, who performed spacewalks to install new instruments and replace aging components. These servicing missions extended Hubble's life and improved its capabilities, allowing it to continue making groundbreaking discoveries. The James Webb Space Telescope, launched in December 2021, is Hubble's successor. Webb is larger and more powerful, with a primary mirror over 21 feet in diameter, more than double the size of Hubble's. It observes primarily in the infrared, allowing it to see through dust clouds and detect the faint heat signatures of distant objects. Webb orbits the Sun at a point called Lagrange 2, about 1 million miles from Earth, where it is shielded from the Sun and Earth's heat, allowing its sensitive instruments to operate at extremely cold temperatures. Webb's mission is to study the earliest galaxies, to observe the formation of stars and planets, and to search for signs of life in the atmospheres of exoplanets. Its first images, released in 2022, were stunning, revealing galaxies, nebulae, and star-forming regions in unprecedented detail. Webb represents a new era in astronomy, a tool that will help answer some of the most profound questions about the universe. Exoplanets, planets orbiting stars other than our Sun, were once purely theoretical. No one knew if they existed or how common they might be. That changed in the 1990s when astronomers developed techniques sensitive enough to detect them. Today, we know of thousands of exoplanets, and the number is growing constantly. They come in every size and type: giant planets larger than Jupiter, small rocky worlds like Earth, planets with thick atmospheres, planets with no atmosphere at all, worlds that orbit close to their stars and are scorched by heat, worlds that orbit far away and are frozen. Some exoplanets orbit in the habitable zone, the region around a star where temperatures are just right for liquid water to exist on the surface. These are the planets that interest scientists the most, because water is essential for life as we know it. Studying exoplanets is difficult because they are incredibly far away and very faint compared to their stars. Astronomers detect them indirectly by observing the tiny wobble a planet causes in its star's motion, or by measuring the slight dimming of starlight when a planet passes in front of its star. More advanced telescopes, like the James Webb Space Telescope, can analyze the light passing through an exoplanet's atmosphere, searching for chemical signatures of water, oxygen, methane, or other molecules that might indicate the presence of life. The search for life beyond Earth is one of the most exciting frontiers in science, and exoplanets are at the heart of that search. The question of whether we are alone in the universe has fascinated humanity for millennia. Every culture has myths and stories about beings from the sky, visitors from other worlds. Today, the search for extraterrestrial life is a serious scientific endeavor. Scientists search for microbial life on Mars, for signs of life in the oceans beneath the icy crusts of moons like Europa and Enceladus, and for signals from intelligent civilizations among the stars. The search for extraterrestrial intelligence, or SETI, uses radio telescopes to listen for signals that might be transmitted by advanced civilizations. So far, no definitive signals have been detected, but the search continues. The discovery of even simple microbial life on another world would be one of the most profound discoveries in human history. Proof that life is not unique to Earth, that it can arise wherever conditions are suitable. It would raise countless questions. How did life begin? How common is it? What forms can it take? The search for answers is one of the driving forces behind space exploration. The moons of Jupiter hold particular fascination in the search for life. Europa, one of Jupiter's largest moons, is covered in a thick layer of ice. Beneath that ice, scientists believe there is a global ocean of liquid water, kept warm by tidal forces from Jupiter's immense gravity. Based on measurements and models, this ocean could be anywhere from 40 to 100 miles deep, potentially containing more water than all of Earth's oceans combined. Where there is liquid water, there might be life. NASA is planning a mission called Europa Clipper, scheduled to launch in the mid-2020s, that will fly by Europa multiple times, using radar to peer through the ice and study the ocean below. Another of Jupiter's moons, Ganymede, also appears to have a subsurface ocean. These hidden oceans, far from the sun's warmth, represent environments where life might exist in forms we have never imagined. Saturn's moon Enceladus is another promising location. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, discovered geysers erupting from cracks near Enceladus's south pole. These geysers shoot water vapor and ice particles hundreds of miles into space. Chemical analysis of the particles revealed the presence of organic molecules and evidence of hydrothermal activity on the ocean floor, similar to the deep-sea vents on Earth where life thrives in total darkness. Enceladus is small, only about 300 miles in diameter, but it might harbor one of the most exciting discoveries in astrobiology. Future missions could fly through the geysers, collecting samples and analyzing them for signs of life, all without having to land on the surface or drill through the ice. Titan, Saturn's largest moon, is unlike any other moon in the solar system. It has a thick atmosphere, thicker than Earth's, composed mostly of nitrogen with clouds of methane. The surface is hidden beneath these clouds, but radar observations from Cassini revealed lakes and rivers of liquid methane and ethane, vast dune fields of organic molecules, and a landscape shaped by processes remarkably similar to Earth's water cycle, except with methane instead of water. Titan's surface temperature is minus 290 degrees Fahrenheit, far too cold for liquid water, but the abundance of organic chemistry makes it fascinating to scientists studying the origins of life. In 2005, the Huygens probe, built by the European Space Agency, descended through Titan's atmosphere and landed on the surface, sending back the only images we have from the surface of a moon other than our own. The images showed a dim, alien world, with rocks of water ice and a hazy orange sky. Titan is a place where the chemistry of life might be happening in ways completely different from anything on Earth. The asteroid belt, located between the orbits of Mars and Jupiter, is a region filled with millions of rocky bodies, remnants from the early solar system that never coalesced into a planet. Some asteroids are small, just a few feet across. Others are hundreds of miles in diameter. Ceres, the largest object in the asteroid belt, is so big it is classified as a dwarf planet. The Dawn spacecraft, launched by NASA in 2007, visited both the asteroid Vesta and Ceres, orbiting each and studying their surfaces in detail. Ceres surprised scientists with bright spots that turned out to be deposits of salt left behind when water evaporated from the surface. There is evidence that Ceres may have a subsurface ocean, or at least pockets of briny water. The asteroid Bennu, visited by NASA's OSIRIS-REx mission, is a carbon-rich asteroid that may contain organic molecules and water locked in its minerals. In 2020, OSIRIS-REx collected a sample from Bennu's surface, and in September 2023, that sample was returned to Earth, providing scientists with pristine material from the early solar system to study in laboratories. Asteroids are time capsules, preserving conditions from over 4 billion years ago when the solar system was forming. Studying them helps us understand where Earth and the other planets came from. Some asteroids pose a potential threat to Earth. Throughout history, large asteroids have struck our planet, causing enormous damage. 66 million years ago, an asteroid about 6 miles wide slammed into what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs, triggering wildfires, tsunamis, and a cloud of dust and debris that blocked out the sun for years. The resulting climate change led to the extinction of the dinosaurs and about 75% of all species on Earth. Smaller impacts have occurred more recently. In 1908, an asteroid or comet exploded over Tunguska, Siberia, flattening 800 square miles of forest. In 2013, a meteor about 60 feet in diameter exploded over Chelyabinsk, Russia, with the force of about 30 Hiroshima bombs. The shockwave shattered windows across the city, injuring over 1,000 people. These events remind us that space can be dangerous, that Earth is not isolated, but part of a dynamic solar system where collisions happen. To protect Earth from asteroid impacts, scientists are working on detection and deflection strategies. Telescopes scan the sky, cataloging asteroids and calculating their orbits to determine if any might cross Earth's path. Most asteroids that could cause significant damage are now known and tracked, though smaller ones, like the Chelyabinsk meteor, can still go undetected until it is too late. If an asteroid is found to be on a collision course with Earth, several options exist for deflecting it. One method is the kinetic impactor, essentially ramming a spacecraft into the asteroid to change its velocity slightly. A small change, applied years in advance, can be enough to make the asteroid miss Earth. In September 2022, NASA tested this concept with the DART mission, Double Asteroid Redirection Test, which deliberately crashed a spacecraft into the small moon of an asteroid called Dimorphos. The impact successfully changed Dimorphos's orbit, proving that the technique works. Other proposed methods include using a spacecraft's gravity to gently tug an asteroid onto a different path, or even using nuclear explosions, though not to destroy the asteroid, but to vaporize material on its surface, creating thrust that pushes it away. Protecting Earth from asteroids is one of the practical benefits of space exploration, a reason to keep watching the skies. The history of women in space is filled with both accomplishment and struggle. Valentina Tereshkova became the first woman in space on June 16, 1963, when she orbited Earth aboard Vostok 6. She was 26 years old, a textile factory worker and amateur parachutist, selected from among hundreds of candidates. Her flight lasted almost 3 days, during which she completed 48 orbits. Tereshkova's achievement was groundbreaking, but it would be nearly 20 years before another woman flew in space. The Soviet Union did not send another female cosmonaut until 1982. In the United States, the original Mercury 7 astronauts were all men, and early NASA programs excluded women, despite the fact that several female pilots had undergone the same rigorous medical and psychological tests as the male astronauts and passed. These women, sometimes called the Mercury 13, were not given the opportunity to fly. It was not until 1983 that Sally Ride became the first American woman in space aboard the Space Shuttle Challenger. Since then, women have played increasingly important roles in space exploration as astronauts, engineers, mission controllers, and scientists. Eileen Collins became the first female shuttle pilot in 1995 and the first female shuttle commander in 1999. Peggy Whitson holds the record for the most cumulative time in space by an American astronaut, 665 days across 3 missions. Christina Koch and Jessica Meir conducted the first all-female spacewalk in October 2019. NASA's Artemis program aims to land the first woman on the Moon, a milestone that will mark another step toward equality in space exploration. Diversity in space agencies is expanding. Astronauts from dozens of countries have flown in space, representing a wide range of cultures, backgrounds, and perspectives. The first African American in space was Goyon Bluford, who flew aboard the Space Shuttle Challenger in 1983. Mae Jemison became the first African American woman in space in 1992. The first Hispanic American astronaut was Franklin Chang Diaz, who flew on 7 shuttle missions, tying the record for the most space flights. The first Chinese astronaut, Yang Liwei, flew in 2003, making China the 3rd country to independently launch a human into space. India, Japan, Canada, and numerous European nations have sent astronauts to space as part of international collaborations. The United Arab Emirates sent its first astronaut, Hazar al-Mansouri, to the International Space Station in 2019. Space exploration is becoming a truly global endeavor, uniting people from all over the world in the pursuit of knowledge and discovery. China's space program has made remarkable progress in recent decades. After launching its first astronaut in 2003, China has conducted multiple crewed missions, developed its own space station called Tiangong, and successfully landed robotic missions on the Moon and Mars. In January 2019, the Chang'e 4 mission became the first spacecraft to land on the far side of the Moon, a region that always faces away from Earth and is difficult to access because of the lack of direct communication. Chang'e 4 deployed a rover called Yutu-2, which has been exploring the lunar surface for years, far exceeding its expected lifespan. In May 2021, China landed the Zhurong rover on Mars, making it only the 2nd country to successfully operate a rover on the Red Planet. The rover explored for nearly a year before entering hibernation in May 2022 as Martian winter and dust storms approached. China has announced ambitious plans that include establishing a research station on the Moon, with goals to send astronauts there potentially by the end of this decade, though the exact timeline continues to evolve. The country's rapid advancement in space technology is reshaping the landscape of space exploration, adding a new dimension to international competition and cooperation. Cooperation in space has a long history despite political tensions. During the Cold War, the United States and Soviet Union were fierce rivals, competing in the space race as part of a broader struggle for global influence. Yet even then, there were moments of collaboration. In 1975, an American Apollo spacecraft and a Soviet Soyuz spacecraft docked in orbit, and astronauts and cosmonauts shook hands in space. The Apollo-Soyuz test project was a symbol of détente, a thaw in relations between the two superpowers. It demonstrated that cooperation in space was possible, even when nations disagreed on Earth. Today, the International Space Station is the ultimate expression of that cooperation. American astronauts and Russian cosmonauts live and work together, relying on each other for their safety, and success. Despite political disagreements between their governments, the crew members maintain professional and often warm relationships. The station has remained operational through international crises, a testament to the enduring value of cooperation in space. European, Japanese, and Canadian astronauts also contribute to the station's operations, making it a truly international effort. The economics of space exploration are changing. Launching satellites was once the domain of governments, but today it is a thriving commercial industry. Companies launch satellites for communication, navigation, Earth observation, and scientific research. The rise of small satellites, some weighing only a few pounds, has made access to space more affordable. Constellations of thousands of small satellites are being deployed to provide global internet coverage, bring connectivity to remote regions, and monitor Earth's environment in real time. SpaceX's Starlink constellation already consists of thousands of satellites, and other companies are planning similar networks. These constellations are controversial because they can interfere with astronomical observations, creating bright streaks in telescope images and radio interference. Astronomers and satellite operators are working together to find solutions, such as darkening satellites or adjusting orbits to minimize impacts on science. Manufacturing in space is an emerging industry. The microgravity environment offers unique opportunities for producing materials and products that cannot be made on Earth. Crystals grown in space are more uniform and defect-free than those grown on Earth, which is valuable for pharmaceuticals and electronics. Fiber optic cables made in microgravity are clearer and more efficient. Companies are exploring the possibility of manufacturing organs and tissues in space, where cells can grow in 3 dimensions without the interference of gravity. These space-manufactured products could have enormous benefits for medicine, technology, and industry. The International Space Station serves as a laboratory for these experiments, and private companies are planning their own space stations dedicated to manufacturing and research. The concept of space elevators has fascinated scientists and engineers for decades. A space elevator would be a cable anchored to Earth's equator and extending into space, with a counterweight beyond geostationary orbit. Vehicles could climb the cable using electric motors and reach space without the need for rockets. The idea is appealing because it would dramatically reduce the cost of reaching orbit. However, building a space elevator presents enormous challenges. The cable would need to be over 22,000 miles long and strong enough to support its own weight while resisting the forces of wind, weather, and orbiting debris. No material currently exists that combines the necessary strength and lightweight, though carbon nanotubes show promise. Even if the material problem is solved, there are questions about how to manufacture and deploy such a cable, how to protect it from damage, and how to ensure safety. Space elevators remain in the realm of theoretical concepts, but they represent the kind of ambitious thinking that drives innovation. Space hotels are no longer pure science fiction. Several companies are developing plans for commercial space stations that would offer accommodations for tourists, researchers, and even filmmakers. These stations would aim to provide larger, more comfortable living spaces than current spacecraft, with amenities designed to make the experience enjoyable. Imagine floating in a room with large windows, gazing at Earth below, or experiencing the thrill of microgravity in a recreational area designed for zero-G sports and activities. If development proceeds as planned, the first space hotel modules could potentially be launched within the next decade, though such timelines in the space industry often shift. While the cost will initially be extremely high, limiting access to the wealthy, the hope is that as technology improves and competition increases, prices might eventually drop, making space tourism accessible to a broader audience. Mining the moon and asteroids could provide the resources needed for future space exploration. The moon's surface contains oxygen locked in rocks, water ice in permanently shadowed craters, and rare earth elements valuable for electronics and manufacturing. Extracting and processing these resources could support a permanent lunar base, providing fuel, water, and building materials without having to launch everything from Earth. Asteroids may be even richer in resources. Some are believed to contain vast amounts of metals like iron, nickel, platinum, and gold. Estimates suggest that a single metallic asteroid could potentially contain metals worth trillions of dollars, though the actual economic value would depend on factors like extraction costs and market effects. Mining asteroids is technically challenging, requiring spacecraft to rendezvous with a tumbling rock, extract material, and either process it in space or return it to Earth. Several companies are working on the technologies needed for asteroid mining, and while it may be decades before it becomes economically viable, it represents a future where space resources might support both exploration and industry. Terraforming Mars, the process of transforming the planet to make it more Earth-like, has been proposed as a theoretical long-term goal by some scientists and visionaries. The concept involves attempting to warm the planet, thicken its atmosphere, and introduce water and vegetation, with the ultimate aim of creating a world where humans could potentially live without spacesuits. Various proposals have been suggested, including releasing greenhouse gases to trap heat, melting the polar ice caps to release carbon dioxide and water vapor, importing ammonia from comets or moons to add nitrogen to the atmosphere, and using genetically engineered organisms to produce oxygen. However, terraforming Mars would require technologies we don't yet possess, would take centuries or even millennia, and would demand resources and commitment on a scale never before attempted. Many scientists question whether it is even possible with current understanding of planetary science, and others debate whether it would be ethical to fundamentally alter another planet, even one that appears lifeless. Still others see it as part of humanity's potential future, a way to ensure our survival by becoming a multi-planetary species. Terraforming remains highly speculative, a vision of a distant future that may or may not be achievable, but it reflects the human drive to explore, to adapt, and to imagine new possibilities. The idea of generation ships, spacecraft that travel for centuries carrying multiple generations of passengers, has been explored in science fiction and scientific thought experiments. If humanity wants to reach other star systems, which are light years away, Current propulsion technology would require journeys lasting hundreds or thousands of years. A generation ship would be a self-contained world, large enough to support a stable population with life support systems, agriculture, recycling, and infrastructure for education, healthcare, and governance. The passengers who boarded would know they would never see the destination. Their children, grandchildren, and great-grandchildren would live their entire lives aboard the ship. Only distant descendants would arrive at the new world. The social, psychological, and technical challenges of such a voyage are staggering. Could a society function for centuries in isolation? How would they maintain their culture, knowledge, and purpose? What if they arrived to find the destination unsuitable? Despite these challenges, generation ships represent one possible path to interstellar exploration, a way for humanity to spread beyond the solar system. Faster-than-light travel remains firmly in the realm of science fiction. According to Einstein's theory of relativity, nothing with mass can accelerate to the speed of light, let alone exceed it. As an object approaches light speed, its mass effectively increases, requiring ever more energy to accelerate further. Reaching light speed would require infinite energy, an impossibility. This does not stop scientists from exploring theoretical concepts that might allow faster-than-light travel without directly violating relativity. The Alcubierre drive, proposed by physicist Miguel Alcubierre, is one such idea. It suggests the possibility of creating a bubble of space-time around a spacecraft, contracting space in front of the ship and expanding it behind, theoretically moving the bubble faster than light, while the ship in turn remains stationary relative to the bubble. The concept is mathematically consistent with relativity in a very specific theoretical framework, but it would require exotic matter with negative energy density, something that has never been observed and may not exist in nature. Even if such matter could somehow be created or found, the energy requirements would be beyond anything we can currently imagine. For now, faster-than-light travel remains a fascinating thought experiment, rather than a realistic possibility. But the fact that scientists seriously consider such ideas shows the human determination to explore every theoretical avenue. The Fermi paradox asks a simple yet profound question. If the universe is so vast and old, with billions of galaxies each containing billions of stars, many with planets in habitable zones, why have we not detected any signs of intelligent alien civilizations? This question, posed by physicist Enrico Fermi, has no definitive answer, but many hypotheses have been proposed. Perhaps intelligent life is extremely rare. Perhaps civilizations tend to destroy themselves before they develop interstellar travel. Perhaps they exist, but are too far away for us to detect. Perhaps they are deliberately avoiding contact. Perhaps we are looking in the wrong way, listening for radio signals when advanced civilizations use communication methods we cannot imagine. Or perhaps, most unsettling of all, we are alone, the only intelligent species in a universe otherwise filled with silence. The Fermi paradox reminds us how little we know and how much mystery still surrounds the question of life beyond Earth. Throughout all these facts, one theme emerges. Space exploration is an expression of who we are as a species. We are curious. We wonder what lies beyond the horizon, beyond the sky. Oh my, beyond the limits of our world. We are builders. We create tools and machines to carry us where our bodies cannot go. We are storytellers. We look at the stars and imagine what might be out there, weaving narratives of adventure and discovery. And we are survivors. We strive to ensure that our species endures, that our knowledge and culture persist, that the light of consciousness does not go out. Every rocket launch, every mission, every image sent back from a distant world adds to the story of humanity reaching outward. So as you close your eyes tonight, think of the astronauts floating aboard the International Space Station, looking down at Earth, seeing no borders, only the shared home of all humanity. Think of the rovers on Mars, alone on a distant world, exploring terrain that has never known footprints. Think of the Voyager spacecraft, still journeying through the dark, carrying golden records with sounds and images from Earth, messages to anyone who might find them in the distant future. Think of all the missions planned, the dreams yet to be realized, the discoveries waiting to be made. Let the vastness of space embrace you. Let the silence between worlds calm your racing thoughts. The universe is patient. It has existed for nearly 14 billion years. It will continue long after we are gone. But right now, in this moment, we are here, aware, looking up, reaching out, asking questions, seeking answers. Space is not a void. It is full of wonder, full of possibility, full of light from distant stars that began their journeys when the universe was young. Those photons have traveled across unimaginable distances to reach your eyes, to tell you their story, to remind you that you are connected to everything, to the atoms forged in stars, to the planets circling distant suns, to the great cosmic dance that has been unfolding since the beginning of time. Rest now. Dream of the stars. Dream of the future. Dream of the day when humanity walks on Mars, when we discover life on another world, when we understand our place in the cosmos a little better. The journey continues even as you sleep. Missions are being planned. Rockets are being built. Scientists are analyzing data. Engineers are solving problems. And somewhere above you, right now, the International Space Station is passing overhead. A bright point of light carrying people who dared to leave Earth, who chose to live among the stars. If you've enjoyed this journey through the history and future of space travel, I'd be grateful if you'd like and subscribe. It helps others find their way here, fellow travelers looking for calm in the vastness of the universe. Share your thoughts in the comments if you wish. What fact surprised you? What aspect of space exploration moves you most? But for now, let it all go. Let the weight of Earth hold you gently. Let your breathing slow to the rhythm of orbits, steady and eternal. The stars are still shining. The universe is still expanding. And you, a small part of this grand cosmos, are exactly where you need to be. Sleep well. Dream of the infinite. And remember that we are all made of stardust, children of the universe, forever reaching toward the light. Good night.